Hello everyone, welcome to our 7th video for our video lecture series on social statistics basics, and for this video we'll talk about different tests for correlation. So this will be a relatively shorter video, and in here we'll be talking about reviewing the different considerations for choosing bivariate statistics, just to differentiate this with the discussions we had on tests for difference. And then we'll be defining what correlation means, basically how it's commonly understood when we talk about it in the context of social research. And then we'll talk about Pearson R correlation and Spearman correlation. What are the values that we have to look out for and how do we interpret them? And then we'll also be talking a little bit about chi-square statistics. So if you remember, this is the list of considerations that we need to ask in order for us to identify which inferential statistical tool we're going to use in order to test the hypothesis. So in relation to doing correlations, what would be the answers to this question in order for us to identify whether we're going to do a correlation test? Okay, since we are still in the realm of bivariate statistics, we're still going to be looking at hypotheses that only test one variable pair at a time. So bivariate, two variables, one independent and one dependent variable. So let's answer that now. So how many dependent variable or outcome variables? One. And then for the IV or predictor variables, that's one. One pair per test. Right? Because there are tests that look at relationship among variables, and then it can be more than two at a time. But for the correlation tests we're just going to use one pair at a time. Now for correlational tests, the dependent variable in terms of their measurement, the level of measurement, usually they assume continuous variables, no? So, yon. And then for the independent variable, also, it should be also continuous. So, usually when you talk about correlational tests, they have to be both continuous, at least most of the time. They have to be continuous variable. Later on, we'll learn that there are schools of thought wherein you can do a non-parametric test of correlation with an ordinal variable, but we'll discuss that later. So, the type of correlational test will differ based on the assumptions of parametric test, no? So if it's okay for parametrics, then we use Pearson R. And if it's not, it did not meet the requirements for a parametric test, then we're going to use a Spearman rho, right? So let's just redefine, every time we hear the word correlation. So it's a statistical technique that used to describe the relationship between continuous variables. So the outcome variable or the dependent variable is continuous. The independent variable or the dependent variable is continuous. Some schools of thought accept ordinal variables because they also manifest directions. Some schools of thought also mention about the term point biserial. So point biserial is when your independent variable has two outcomes. It's a categorical variable with two outcomes. Some schools of thought suggest that you can actually do correlation with this. If the correlation coefficient is negative, it means that there's a negative relationship, and then if it's positive, it's a positive relationship. Although we don't use that in the department, you might be coming across that in other studies that they have used point biserial. Also the same thing with ordinal outcomes. If both or at least one is an ordinal outcome, a correlation test can be used. But in our department, we're very conservative. We only make use of correlational tests when they're both continuous. And basically, we look at two outcomes here. Three outcomes actually. So we're looking at three outcomes here. First, we want to see if the correlation is significant. So this is the function of the p-value. Next, we want to see the direction of the relationship, whether or not it's positive or negative, and usually the sign of the R value. right? So this is the function of the R value. And then number 3 is the magnitude of the relationship, which is basically can be from -1 to +1, right? And then of course 0 means no relationship. Now, we also have to look at correlation tests as having linear relationships. When we say that certain variable pairs have linear relationship, it means that they assume this kind of relationship right here. So when it means that the direction is when the direction is just really just going one direction, and throughout, and then until you get to the maximum or to infinity of whatever value that is, the direction and the magnitude will kind of determine how the other variable will react when one variable moves across that line. So that's linear relationship. And usually when you talk about linear relationship, it's usually represented by a line. So for example, in this case, the salary received by the persons who are into direct selling is very much linearly correlated with the merchandise that they are able to sell. So the higher sales, the higher number of sales that you make, the higher number of sales, the higher your salary would be, especially if it's your salary is based on commissions. However, not all relationships in reality are linear. So there are many linear relationships, like for example, the amount of hours of sleep and the amount of hours awake in the day. So that's a perfectly linear relationship because there are only two outcomes there, right? You're awake or you're asleep. So it's directly linear relationship, So the more hours of sleep a day, the lesser hours of being awake in the same day, right? So that's very obvious. Or another example of a linear relationship would be, let's say, when you have the higher number of calories that you intake, controlling for the effect of other things, right? You will gain more calories, The more grams that you eat, the more calories that you have to intake in your body, So that's an example of a linear relationship. In behavioral sciences, the linear relationships may not be as straightforward as we think they are, because most of our behaviors in our social, especially social gradients in our life, they react very differently based on context. But probably let's look at, for example, the more, let's say the higher level of anxiety that you have, then the higher levels of psychosomatic symptoms you have. So psychosomatic means feeling physical symptoms because of stress. So the higher level of anxiety, the higher levels of stress, right? Or for example, the more positive you evaluate your relationships with the family, the higher level is your social well-being. So that's another example of a linear relationship. So the higher you rate your family relationship, the higher your appraisal for your social well-being. But there are also other relationships which are curvilinear, meaning they're like this, right? So it can start with when the variable is low. So when x is low, y is high, and then there's a certain point that it dips into its lowest in the middle of x, and then eventually it will pick up again. So an example would be these variables, right? So we have protective voice belief. So it means that when it appears here that when a person has low job satisfaction, the more likely they feel like they need to have their voice heard by whoever runs the company. The same, and that value goes lower as the job satisfaction becomes, closer to the mean. And then when it goes after the mean, it starts to go high again. When your job satisfaction is high, you also have a sense that you are being heard, or your voice is being heard in that company. So that's an example of a curvilinear relationship. Another example of a curvilinear relationship would be, for instance, your throughout your life, no, if your x-axis is your years in life, and then your y-axis is the number of times you meet with your siblings, no. So there's a study that shows that your proximity to your siblings when you are young is very high, and then as you go to your young adulthood years, you try to break off your family, and so your proximity to your siblings will be lesser. And then when you grow older, that's the time you also start to come back to, having more relations or having more interactions with your siblings. So that's another example of a curvilinear relationship. However, we will not be able to run curvilinear relationship tests. It kind of is a more complicated statistical test, so we won't be able to test that. We will be more interested in linear relationships. So as I said, aside from identifying whether or not it's a significant relationship or it's a significant relationship, is that we also have to know the direction of the relationship, and there are two directions. We have the positive or the negative relationship. No, so again, when you do your correlation, each one represents a data point. So this one is a data point per person. So one person, when you plot the person in the line with the x-axis as your dependent variable and your y-axis as your independent variable, you would see here that when you plot them, they will sort of have a this kind of graph. So so this is called your scatter plot diagram. Scatter plot diagram. So this scatter plot diagram basically shows you where each data points are based on the IV and the DV, or the variable pairs, and then you will see here yung all the data points. So in the data points, when you look at where most of them lie, you can actually draw a line, and that's why it's linear relationship. So if the line is like this, then it's a positive relationship. So for example, the higher intelligence, the higher the grade point average. For example, here, the higher the level of stress, the lower the level of immune functioning. So this one is a negative relationship. This one is a positive relationship. So there's a direct relationship when it's a positive relationship. So when independent variable goes high, the dependent variable goes high, or vice versa, right? In the negative relationship, when there's an inverse relationship, when independent variable is high, the dependent variable goes low, or vice versa, right? So that's an example. So aside from looking at the p-value telling you the significance of the relationship, if it's less than 0.05, you also have to look at the R value, or we usually call the correlation coefficient. So the correlation coefficient basically tells you two things. One, it tells you the direction of the relationship, and we've discussed that. It's positive or negative, but it also tells you the magnitude of the relationship. So the magnitude of the relationship can vary from +1 to -1, right? So it will tell you how closely are the two correlated. The sign of the coefficient tells us whether it's positive or negative. I said that earlier. And then the numerical part describes the magnitude of the relationship. So the closer it is to 1, the stronger the relationship. So syempre, if it's positive, it's a positive relationship. It's negative relationship. And then if the correlation is 0, which rarely happens, it's non-existent, meaning the two variables, there's no pattern emerging from the two variables. But before I continue, I would like to always remind you that correlation is not causation, right? So if the two variables empirically demonstrate some form of significant correlation, it doesn't necessarily mean that variable A is the cause of variable B. There are so many statistical tests and there's a different research design that you need to do to actually establish a causation. So if you are just measuring variables and observational, no, you're just doing an observational analysis of variables, meaning you've collected variable A and collected variable B, you did not do any manipulation, you did not have any form of, you did not include time, no, in the mix, no, you were not able to control for the effect of other variables, then you are just saying that maybe there is a correlation between them. There might be an explanation why they behave the same way, or they behave differently, or that they are closely linked with each other. They may be theoretical assumptions about that, but we cannot say exactly when you do correlational tests that variable A causes variable B. So for me, it's very important that you really have to be very careful when you report the results, because you cannot say, for example, if you were able to establish a correlation, let's say, between family social support and, let's say, mental well-being, you were able to find that. You cannot say, when you did only a correlation, that family social support affects well-being. You can kind of infer that, but when you report that, it's only just positively correlating each other, and you can kind of infer or imply that maybe these are the mechanisms to which A and B are correlated to each other, but you cannot say for sure that that they are affecting each other, especially if the theory does not support that. I'll give you an example. So there was a study that was done before, and this is a classic example of that, wherein per year, the number of data collected for the drowning per year was correlated with the amount of movies that was seen, or that was released. I don't know the name of the artist. There was a specific artist. I think that's Sylvester Stallone, if I'm not mistaken. So there was parang a decade wherein every year the number of drowning incidents was found to be positively correlated with the amount of movies that Sylvester Stallone had released per year. So, but that's a correlation that can, that you cannot say immediately, because statistically there is a correlation when they just plotted it out, but theoretically it makes no sense, no. So sometimes, no, we might be bumping into statistical correlations, but they're not, they might not, if there's no theoretical connections, then we cannot really say that A caused B. Can we use statistics to actually determine the cause of that A is actually the cause of B? Yes, definitely we can, but not with this specific type of statistic. There are more complicated statistical tools that we need to use, like, for example, path analytic studies, or we have to design actual experiments for us to be really certain that, yes, we're able to say that A caused B. But for correlation, A is correlated with B. A is related to B, but A not necessarily caused B, especially if your design is cross-sectional, meaning you collected data at the same time. Alright, so very important, especially when you're reporting your findings and presenting your result. So, in the hypothesis you're relating IV and DV and they're both continuous, and you pass the tests for parametric test, then you use a Pearson R correlation. Okay, so what are the values to check? So in the statistical tool, in the Jamovi, you look at first at the p-value. So if the p-value is 0.05, then you reject the null hypothesis, meaning that there is a significant relationship. But you go further and you look at the R value and you check for the direction, whether it's positive or negative, and then you check for the magnitude. You interpret the magnitude. So this is the formula for
Pearson R, just in case you want to look at it. But I said, we're going to use Jamovi anyway. Now, if both our IV and DV are both continuous, and then we did not pass the parametric requirement, so we use a non-parametric. So we use spearman rank or spearman row. So yun yung ginagamit natin if it's not parametric. Or again, like I said, if at least one of the two variables are ordinal, you can also use spearman in other schools of thought. But for our department, if it's ordinal, you have to use ANOVA if it's parametric, or Kruskal-Wallis if it's non-parametric. So I hope that's very clear. So what are the different values to check? Same thing, it will also generate a p-value. And then if it's less than 0.05, then you reject the null hypothesis. And then you check the R value or the correlation coefficient. And then it will give you a sign and also the magnitude. So how do you interpret the magnitude? So there are, when you go from one text to the next, you can find different interpretations. So we will use this by Dancy and Rildy on psychology. So if it's 1, of course it's perfect, but we rarely see that for behavioral research. So if it's 0.7 to 0.9, then it's a strong relationship. If it's from 0.4 to 0.6, then it's moderate relationship. If it's 0.1 to 0.3, then it's a weak relationship, right? And then of course if it's 0, then there's no relationship. Eventually, when you look at p-value, usually you won't really have to look at the correlation. Remember, you don't have to look at the correlation coefficient if the significance is not established. So I'm going back here. So again, but the values that you have to check is if the p-value is less than 0.05, then you reject the null hypothesis. That's the only time you go to the next step of looking at the correlation coefficient. If it's not significant, meaning if it's 0.05 and above, there's no need for you to interpret the Pearson R or the Pearson R or the Spearman Rowe correlation coefficient, because it's not significant anymore. So most likely it will be a negligible relationship kasi nga it's not significant. So usually if it doesn't reach 0.01 or 0.01, it's not really a good relationship talaga. It's not significant, I mean. So in this video, I talked about the continuous variables. When two continuous variables are being correlated, then we are talking about correlation, and then we talked about negative and positive relationship, linear and curvilinear relationships, and we talked about also how to interpret correlation coefficients and also run tests for Spearman and Pearson R.